week 8 of the engineering thermodynamics course, problem solving session. So previous week we saw about applying first law to a control volume or open system, and then this week we'll extend some more problems on control volume systems, applying first law, and then go to a second law. So before going to numericals, we will see we'll give you a brief idea on second law. So first law states an energy balance, so how energy is getting converted and so on, the balancing of the energies. But we don't know how this energy can be transferred, or how it can be converted, or the path which can be taken, whether is it possible or not. So that is not defined by first law. So that's where the second law comes, and you have two sets of statements which are given by Kelvin, Planck and Clausius, that you cannot convert whatever heat which you are receiving to work. Basically, you cannot have interaction with just one source and produce work. And then without supplying work, the heat from low source cannot be transferred to a higher source. So those were the two statements, and with that that defines a reversible engine, and then how maximum energy which can ever get from a reversible engine, a Carnot engine, and then a refrigerator and a heat pump. So how would you define a coefficient of performance for this? So that's all is covered in second law, and we'll see some problems on this. So starting, I'll start with again continuing some problems on first law for control volume. So first question is, mass loaded piston cylinder is shown in figure, containing air at 300 kilopascal and 17 degrees Celsius with a volume of 0.25 meter cube. I think covered this in the previous class. Okay. So what we have is a 2 meter cube storage tank, contains 95% liquid and 5% vapor by volume of liquefied natural gas at 160 Kelvin as shown in figure. So it may be assumed that liquefied natural gas has the same property as pure methane. So heat is transferred to the tank, and saturated vapor at 160 Kelvin flows into a steady flow heater, which then leaves at 300 Kelvin. The process continues until all the liquid in the storage tank is gone. Calculate the total amount of heat transfer to the tank and the total amount of heat transfer to the heater. So what we have is a storage tank here, which contains initially 95% of liquid and 5% of vapor. So this is by volume, and the temperature at which this liquid is there is at 160 Kelvin, and you have heat which is coming in, because of which the liquid is converting into vapor, and that vapor is coming out at 160 Kelvin and flows to a heater where it is heated to 300 Kelvin. So that is the process. So we need to find out how much is the heat which has to be supplied to the tank, and how much heat is to be supplied to the heater. So that is the idea. So we'll see how to solve this. It's a simple problem. So first, taking the control volume of the tank. So it's a transient system. So you have mass of flow which is coming out and there is no mass flow in. So if you do a mass balance, so m2 minus m1 is equals to m dot e is the mass which is flowing out, and mass 2 is the state of mass in the tank at state 2, and m1 is the mass present initially. So if you apply an energy balance across this control volume of the tank, so what you get is the change in energy. So basically what you have is energy in minus energy out equals the change in the system. So the energy in is your tank, and the energy out is your enthalpy carried by the saturated vapor of methane or LNG which is going out. So Me into He. So Q tank minus Me He equals the change in the internal energy of the system, which is M2 U2 minus M1 U1. So energy in minus energy out equals energy change in the system. So that's what you get in the energy equation. So we need to find out Q tank. So we took the energy out term to the other side. So this the expression you get. Q tank is M2 U2 minus M1 U1 plus Me He, and we know the relation between masses here. So initially, to find out the initial mass which was present, we know the liquid and vapor volumes occupied initially, which is 95% and 5%. So for 160 Kelvin, for methane, from the property table you can find out corresponding to 160 Kelvin your saturated liquid specific volume is 0.00297, and similarly the gas is 0.03935, and what we know here is the volume of the tank is 2 meter cube. So the volume of liquid will be 2 into 0.95 because 95% of the volume is liquid. So 0.95 into 2 is the volume occupied by the liquid, divided by specific volume gives you the mass of liquid, which is 639.73 kilograms. And similarly for gas, the volume occupied is 5%, so 0.05 into the total volume, which is 2, divided by specific volume gives you the mass of vapor to be 2.541. So these are the initial masses of liquid and vapor initially present. So the final volume, the initial mass, so now will be 639.73 plus 2.541, which gives you 642.271 kilograms. So this is the initial mass present in the tank, and then the final mass is when it's totally saturated vapor. So the process continues until all the liquid in the storage tank is gone. So that says that now the tank contains all of vapor. So in that case, the whole volume of 2 meter cube is occupied by saturated vapor LNG at 160 Kelvin. So in that case, your specific volume is again 2 divided by specific volume gives you the total mass of LNG left in the tank when it is fully occupied by vapor. So that gives you 50.826 kg. So that is the final mass. So using this, we know how much mass has exited out. So Me is 642.271 minus 50.826. So that comes out to be 591.445 kilograms. So this is the amount of LNG which has evaporated and converted into saturated vapor and has left the storage tank. So the initial internal energy is M1 U1. So initial mass we know for liquid and vapor. So the saturated liquid internal energy for liquid and saturated internal energy for vapor gives you so 639.73 is the mass of liquid present into internal energy of the liquid, internal energy of saturated liquid plus mass of vapor into internal energy of saturated vapor. So that gives you the initial internal energy to be minus 67,507 kilojoule. And the final internal energy will be the same mass at the final state is 50.826 kg of saturated vapor. So 50.826 multiplied by the saturated vapor internal energy, which is 207.7. So 50.826 into 207.7 minus the initial internal energy, which is 67,507, plus that mass which has exited, which I found out 591.445, multiplied by the saturated vapor enthalpy, that comes out to be 270.3. So adding this up, we get the heat which is supplied to the tank to be 237.931 megajoules. So 237.931 megajoules is the amount of heat which is supplied to the tank to vaporize the liquid. Now we need to find out how much heat has to be supplied to the heater to heat the saturated vapor which is coming into the heater at 160 Kelvin to 300 Kelvin. So to do that, the first is the saturated the gas which is coming in to the heater is at saturated vapor. So the corresponding saturation pressure is to 160 Kelvin is 1593 kilopascal. So this is the pressure at which the LNG vapors, saturated vapor is coming, and the heater, we assume that there is no pressure drop, so there is a constant pressure process. So your pressure at the output also will remain same, 1593 kilopascal, and we know that it is leaving at 300 Kelvin. So the amount of the total heat supplied will be the change in enthalpy of this. So mass into enthalpy difference, because the energy coming in is MEHI, and heat which is added with the heater equals the mass into enthalpy out. So rearranging, this is what we get: the mass of LNG leaving the tank multiplied by the enthalpy difference. So enthalpy corresponding to 1593 kilopascal and 300 Kelvin is 612.9, and similarly 1593 kilopascal and 160 Kelvin, which is a saturated vapor, is 270.3. So this gives you the heat added to be 202.629 kilojoules, megajoules. So 202.63 megajoules. Moving on to next question. A somewhat simplified flow diagram for a nuclear power plant is given in figure. So mass flow rates and the various states in the cycle are shown in the accompanying table. The cycle includes a number of heaters in which heat is transferred from steam taken out of the turbine at some intermediate pressure to liquid water pumped from the condenser on its way to steam drum. The heat exchanger in the reactor supplies 157 megawatts, and it may be assumed that there is no heat transfer in the turbine. So A, assume the moisture separator has no heat transfer between the two turbine sections. Determine the enthalpy and quality H4 and X4. Determine the power output of the low pressure turbine. Determine the power output of the high pressure turbine. Find the ratio of the total power output of the two turbines to the total power delivered by the reactor. So this is the process diagram. So what we have here is, there is a reactor. So we are supplying water to the reactor. It's getting heated up, and we are storing it in the steam drum. And the vapor here is steam is passed to a high pressure turbine, and you are bleeding off some steam from the high pressure turbine and sending it to a heater, and whatever is condensing, you are sending it back to the steam drum. And similarly, you are bleeding off at two places, and then whatever is exiting the high pressure turbine, you are sending it to a moisture separator, and the water is separated here and is taken to a pressure heater, and then the vapor which is leaving the moisture separator is passed to a low pressure turbine, and then the exit of which is sent to a condenser, and then from the condenser liquid is now pumped to different heaters, and you are also adding bleeding of some steams from the turbine and sending it to the heaters. So this is the process diagram, and you have set of points given, the corresponding mass flow rates and pressures and temperature and the enthalpy of each of the state points are given in the table here. So first is question is, assume the moisture separator has no heat transfer between the two turbines. Determine the enthalpy and quality at H4 and X4. So this is the moisture separator. We need to find out the enthalpy and quality at this state here, the the one which is entering the low pressure turbine. So what we know at 4 is, we know pressure is 310 kilopascal, and we know at what it is entering 3. So we know mass, amount of mass, we know pressure and the enthalpy here. So first we'll assume a simplified diagram. So we have high pressure turbine, we have a moisture separator, and then the low pressure turbine. We need to find out the enthalpy and quality at state 4. So this is a simplified diagram. So what we do, so if we apply a control volume across this moisture separator, so doing a mass balance, so M3 is coming in, M4 is going out, and M9 is going out. So M3 equals M4 plus M9. So that is one equation. So we need to find out the mass at 4. So M4 is M3 minus M9. So here M3 is given 62.874 and 9 is 4.662. So that gives you M4 to be 58.212 kilograms per second. So that's the mass at state 4. Now we know our masses at each of the state points. So we know at 3 and 9 the enthalpies as well. So doing an energy balance, so M3H3 equals M4H4 plus M9H9. So that is the energy balance across the moisture separator. So energy coming in, so at stream 3 which is coming into the moisture separator, so M3H3, and which is going out is 4 and 9, so M4H4 and M9H9. So that gives you the energy balance. So we need to find out the enthalpy and quality at state 4. We know the enthalpy at 3 and enthalpy at 9, which is given in the problem. So H4 is M3H3 minus M9H9 divided by M4. M4 we have found out it to be 58.212 kilograms per second. So substituting, we get H4 to be 2673.9 kilojoules per kg. So since we know now H4 and we also know the pressure of H4, so we can find out what is the saturated enthalpy of the vapor and the liquid. If the enthalpy of H4 lies between the saturated liquid and saturated vapor enthalpies, so that says that it is in a two-phase state, and we can find out the quality using the saturated liquid and saturated vapor enthalpies. So using that, we can X4 comes out to be 0.9755. So next question is to find out the work done in the low pressure turbine, power output of low pressure and high pressure turbine. So for low pressure turbine, if you put an energy balance across the low pressure turbine, so similarly doing a mass balance, so M4 equals M5 plus M8, which are 5 and 8 are outgoing streams and 4 is the inlet stream. So M4 equals M5 plus M8, and similarly energy balance here. So work is out, so the energy coming in is M4H4, which equals to the energy going out is M5H5 plus M8H8 plus W, which is the work which is done by the low pressure turbine. So what we get is M5 is M4 minus M8, So we don't know mass of 5, we know 4, we know 8. 4 we have already found out previously. So M4 minus M8 is 58.212 minus 2.772, which gives you 55.44 kilograms per second. So W is again the difference between the inlet and outlet enthalpies streams. So what we get is M4 is 58.212, and similarly enthalpy which we found out, and M5H5 and M8H8. Substituting the values, we get work done by the low pressure turbine to be 22.489 megawatts. And for high pressure turbine, so here too there is no heat transfer, so a similar equation. So if you write the energy equation here, the incoming stream is 2, outgoing streams are 3, so 3, 12 and 17. So M2H2 equals M3H3 plus M12H12 plus M17H17 plus the work which is done by the high pressure turbine, so WHP. So rearranging, this is what we get, and substituting the values here again, which is all given in the table, so it comes out to be 18.394 megawatts. And the final question is, find the ratio of the total power output of the two turbines to the total power delivered by the reactor. So reactor is doing some work and it is heating the steam drum. So that is given to be 157 megawatts. So that is the amount of heat which is supplied by the reactor. So we need to find out the total work done by the two turbines divided by this heat which is supplied by the reactor. So comes out to be for high pressure turbine the work output is 22.489 and low pressure is 18.3894. So summation of that divided by 157, so that comes out to be efficiency of 0.26. So moving on to the next question. The following data are for a simple steam power plant as shown in figure. So you have 7 states given, 1, 2, 3, 4 to 7, and the pressure at each of the states. So at 1 is 6.2, then 6.1, at 2, 3, 5.9, and similarly because of each component there is pressure drops which is given here. What are the pressure drops at each of the state points? And at 6 and at 7 is 0.009 megapascal. So temperature at 2 is 45, and similarly at 3 is 175, 5 is 500, 6 is 490, and 7 is 440. And similarly enthalpies are given. So state 6 has a quality of 0.92 and velocity of 200 meters per second. The rate of steam flow is 25 kilograms per second with 300 kilowatts of power input to the pump. So pump power input is also given. So piping diameters are 200 mm from the steam generator to the turbine. So here the piping diameter is 200 mm and 75 mm from the condenser to the economizer and steam generator. So the only part from steam generator to the turbine is of 200 mm. The rest of it is of 75 mm diameter tubes. So determine the velocity at state 5 and the power output of the turbine. So what we know is at state 6 the velocity is 200 meters per second. We need to find out at state 5 what is the velocity and the power output of the turbine. So at 5 the turbine output, the area, if you calculate the area at state 5 is pi by 4 d square. So d is 200 mm, so 0.2 meter square, so that gives you 0.03142 meter square. And what we know is the flow rate is known, which is 25 kg per second. So at this point, the specific volume is 0.06163 meter cube per kg. So at state 5, corresponding to this pressure and temperature, so 5.5 megapascal and 500 degrees Celsius. So sorry, state 5 is 490. So 490 and 5.5. The specific volume is 0.06163 meter cube per kg. So mass divided by specific volume gives you the volume flow rate. So mass multiplied by specific volume gives you the volume flow rate, divided by area gives you velocity. So a mass into specific volume divided by area. So mass is 25, mass flow rate is 25, multiplied by specific volume, which I found out, divided by the area. So it comes out to be 49 meters per second. So next is the enthalpy at 6. So enthalpy at 6 is what they have given is it's of 0.92 wave fraction, so corresponding to 0.01 megapascal and 40 degrees Celsius. The enthalpy is saturated vapor and the latent heat here multiplied by x gives you the enthalpy at state 6, so 2393.2 kilojoule per kg. So work done in the turbine is applying the first law again. So here, since it has velocity, so we need to take into account the kinetic energy as well, and we neglect the potential energy. So energy in is h5 plus the kinetic energy half mv square minus the enthalpy out into h6 minus the kinetic energy. So we are writing in terms of specific energies, so dividing by mass flow rate throughout. So what we get is H53404, which is already given here, and H6 is 2393.2, and the kinetic energy terms. So it total comes out to be 992 kilojoule per kg. That is the specific work done by the turbine. So the total work done will be mass into 992. So mass is 25 kilograms per second multiplied by 992 gives you 24800 kilowatts or 24.8 megawatts of work which is done by the turbine. You see here even though the velocities are given, the velocity terms contribute very less in terms of energy. So we have 2000 divided by 1000, so that's basically 2 compared to the quantity here. So 992, so it's very small contribution by the kinetic energy. So for the same steam power plant as shown in figure of this previous problem, assume the cooling water comes from a lake at 15 degrees Celsius and is returned at 25 degrees Celsius. Determine the rate of heat transfer in the condenser and the mass flow rate of cooling water from the lake. So going back, you have the same steam so you have the same steam power plant. So what is here is then the condenser. So you are using water from the lake which is coming in at 15 degrees Celsius and is going out at 25 degrees Celsius. So in the process, the steam is getting cooled. So we need to find out how much of mass of water is required in the condenser. So to find that, will apply energy balance here. So we know enthalpy at 6, which you have found out. So and we know enthalpy at 7, which is given at 168. So and we know water. So the corresponding enthalpies to the temperature, and the only unknown will be the mass. So to find that, so first we'll find out what is the velocity at the exit of the condenser. So since the diameter there is pi by 4, it's 75 mm. So the area at the condenser exit is pi by 4 into 0.075 square. So that comes out to be 0.004418 meter square. And the specific volume at this point is 0.001008 meter cube per kg, and the velocity at this state is the mass into specific volume divided by the area. So that comes out to be 5.7 meters per second. So that's a very small velocity, and we have already found out enthalpy at state 6, which is 2393.2 kilojoule per kg. So applying a control volume across the condenser and writing the first law. So again, the energy in is going back to the problem. The energy in is m6h6, or the mass of steam into h6, and the water, cooling water coming in. So mass of water into the enthalpy of water coming in equals the mass while leaving, so m7h7, and the cooling water m water into h water leaving out. So that is the total energy balance. So to find out Q, how much heat is rejected by the steam, so we can assume instead of water that some amount of heat is being rejected, which is carried by the water. So whatever heat is rejected by the steam is carried by the water. So Q is the enthalpies change across the steam inlet and outlet. So Q specific heat rejected is H7 minus H6 plus the kinetic energy term at the inlet and exit of the condenser. So H7 is 168, which is given straight away in the problem. And H6 is 2393.2, and the velocities at exit is 5.7 square minus 200 square divided by 2000, which is converted into kilojoule terms. So what we get is Q rejected heat in the condenser is minus 2245.2 kilojoule per kg, and since the mass flow rate is 25 kg per second, which is given in the problem, so the total heat rejected is 25 into minus 2245.2, which comes out to be 56.13 megawatts of heat which is rejected in the condenser. So this is equal to the enthalpy change in the water, cooling water, so which is equals to m h out minus h in. So the corresponding enthalpies for 15 degrees and 25 degrees, so 25 is 104.9, and for 15 degrees the enthalpy is 63 for atmospheric pressure conditions. So mass comes out to be the total heat divided by the change in enthalpy. So it comes out to be 1339.6 kilograms per second. So this is the amount of water which is required to cool the steam in the condenser. Next question is, we have refrigerant R134A flows at steady state through a horizontal tube having an inside diameter of 0.05 meter. The refrigerant enters the tube with a quality of 0.1, temperature of 36 degrees Celsius, and a velocity of 10 meters per second. The refrigerant exits the tube at 9 bar as a saturated liquid. Determine the mass flow rate of the refrigerant in kilograms per second, the velocity of the refrigerant at the exit, the rate of heat transfer in kilowatt, and its associated direction with respect to the refrigerant. So what is given is, we have a condensing problem. So this, where can you encounter this? So this is similar to your refrigerator, where you are rejecting heat outside. You see in the old refrigerators you have heat exchanger at the back of your fridge. So this is the problem similar to that. You have refrigerant flowing out, so you have vapor which is coming in and which is getting cooled, and ideally we assume that the pressure is constant, there is no pressure drop, so it's an ideal case. So you have vapor which is coming in, which is getting cooled by rejecting heat to the atmosphere. So atmospheric cooling is cooling this refrigerant, and the exit of this heat exchanger, the condenser, you have liquid which is coming out. So you have the similar case problem which is stated here. So we are just a simplified version of it. So what they say is, we have a horizontal tube, and at the inlet we have a two phase which the quality is 0.1. So that means 10% of it is vapor and rest is liquid, and then out you are having saturated liquid, and the inlet they are given the temperature and the velocity, and the diameter is given. We need to find out what is the velocity at the exit, the mass flow rate of the refrigerant, and the rate of heat transfer. So this is the problem. So you have a tube of diameter 0.5, the inlet is given, the refrigerant, and the exit is also given. So mass flow rate is A in V divided by the specific volume. So area is pi by 4 d square, and the velocity at inlet is known. So divided by specific volume will give the mass flow rate. So specific volume at refrigerant and inlet is, because this is in two phase case, so V is Vf1 saturated liquid specific volume plus X into the quality into the difference in specific volume of saturated vapor minus saturated liquid. So at 36 degrees Celsius, from the refrigerant property table, we can find out the saturated liquid specific volume to be 8.59 into 10 power minus 4 meter cube per kg, and the saturated gas specific volume to be 0.0223 meter cube per kg. Substituting in the above expression and substituting X as 0.1, we get specific volume to be 0.003003 meter cube per kg. So with this, now we can find out the mass flow rate. The area is pi by 4 into d square, d is 0.05 meters, so 0.05 square, multiplied by the velocity is 10 divided by the specific volume, which comes out to be 6.54 kilograms per second. So that is the mass flow rate at the inlet. So doing a mass balance, the mass flow rate at inlet will be equal to the one at exit, because the straight tube there is no accumulation of mass anywhere. So whatever mass which is coming into the tube will go out, so mass will remain constant. So substitute here, so we get because the area is constant, so the areas get cancelled out. So velocity at 2 divided by specific volume equals the velocity at 1 divided by specific volume at 1. So we can find out velocity at 2 to be the ratio of specific volumes multiplied by the volume specific uh, velocity at inlet. Since the outlet is at saturated liquid, so we will have a saturated liquid specific volume, which is the same as here, 8576 meter cube per kg. Substituting and solving for exit velocity. So initially here we take the pressure corresponding to 36 degrees Celsius, and that is not equal to 9 bar for R134A. The saturated pressure corresponding to 36 degrees Celsius is 9.12 bar. So we have a pressure drop across the uh, tube. So outlet is at 9 bar. So we will take saturated property corresponding to 9 bar. Here we will take properties corresponding to 36 degrees Celsius. So outlet, the specific volume corresponding to saturated liquid at 9 bar saturated pressure is 0.0008576, so 8.5 in 76 in 10 power minus 4. Substituting here, we get velocity to be 2.86 meters per second. So next is we need to find out how much heat is transferred. So applying an energy balance across this tube. So here energy in is the enthalpy coming in, so a mass into H1, and then which is going out is Q, and then m dot into H2, and also the kinetic energy terms. So substituting here, so this is the first law for the open system. So W and potential energies are neglected. So QCV is m dot H2 minus H1 plus half V2 square minus V1 square. So enthalpy at inlet is HF1 plus X1 into Hg minus Hf. So corresponding to 36 degrees Celsius, Hf and Hg values are 100.25 and 166.15. So substituting enthalpy at 1 will 116.87 kilojoule per kg, and similarly specific enthalpy at saturated liquid refrigerant corresponding to 9 bar from the table is 99.56 kilojoule per kg. So substituting the values here, we get the Q to be minus 113.5 kilowatts. So Q is difference in enthalpy and the difference in potential energy, sorry, kinetic energy. So that comes out to be minus 113.5 kilowatt. So this sign is negative. So that says that heat is rejected to the atmosphere or the surrounding. So enthalpy is reducing, so and because of which you have to reject heat. So if you consider this as system, so Q is rejected. So that's why it's negative. So some more problems on unsteady flow problems for first law. So first is a simple problem for mass balance. So we have an empty bathtub, has its drain closed and is being filled with water from the faucet at a rate of 10 kg per minute. After 10 minutes, the drain is opened and 4 kg per minute flows out, and at the same time the inlet flow is reduced to 2 kg per minute. So plot the mass of the water in the bathtub versus time and determine the time from the very beginning when the tub will be empty. So there are three things which is happening. So first is initially the tub is empty and the drain is closed. So you're opening the tap or faucet and you're letting it fill for 10 minutes. Till that time your mass flow rate is 10 kg per minute, which is coming into the tub. Then after 10 minutes the drain is opened. The same time you are reducing the flow rate, inlet flow rate, to 2 kg per minute. So by this time there is some water which is filled in the bathtub, and there is because of the drain being opened, the water is flowing out at 4 kg per minute, and now the water coming in is also reduced to 2 kg per minute. So but from start to at what point of time will the tub become empty? So that's the question, and we need to we plot how the mass is varying in the bathtub. So we'll see how to solve this. So first is again we'll just like the energy balance and mass balance, we'll apply the mass balance here. The mass coming in minus the mass going out is the mass change in the system. So initially for the first 10 minutes there is no mass which is going out, there is only mass which is coming in. So whatever mass is coming in is getting accumulated in the system. So the change in mass of the system is equal to the mass which is coming in. So dmCV by dt, so the rate of change of mass in the system, is the mass flow rate, which is equal to 10 kg per minute. So if you integrate this, so you get the total mass which is accumulated for 10 minutes is mass flow rate into, because the mass flow rate is constant at 10 kg per minute, so it's multiplied by delta t, the interval. So 10 kg per minute multiplied by for 10 minutes, which gives you 100 kgs. So for 10 minutes the bathtub was contained 100 kg of water. So this is how initially the mass flow will vary. So initially it was at 0 time, and from 0 it is going up to 100 kg per 100 kgs for 10 minutes. So at this point now two things are happening. One, the mass flow rate is reduced to 2 kg per minute, and the drain is open and the water is flowing out of the bathtub at 4 kg per minute. So the net which is happening is my 2 kg of is coming in, 4 kg is going out. So equivalent is 2 kg going out. So there is a net drop of 2 kg, so minus 2. So the mass rate of change of mass flow rate. So initially from 10, it is now it has become minus 2 at 10 minutes. So we need to find out at what time this mass will become 0. So from this point, so it will reduce at a constant mass of 2 kg per minute reduction. So again applying the mass balance equation, so mass coming in minus mass going out equals the mass rate of change of mass in the system. So dmCV by dt equals mass in minus mass out. So mass in is 2 kg per minute and mass out is 4 kg per minute. So dmCV by dt is minus 2 kg per minute. So again integrating this is delta m2 is m dot net into delta t2. So delta m is now we need minus 100. So reduce it by 100. So minus 100 divide by -2 gives you delta T2 as 50 minutes. So it requires 50 minutes for the tub to be empty. But what is asked is at total what time from the start. So initially it was 10 minutes and now it has taken 50 minutes. So total it comes out to be 60 minutes or 1 hour. Next question. You have a nitrogen gas is contained in a rigid 1 meter cube tank initially at 10 bar and 300 Kelvin. So heat transfer to the contents of the tank occurs until the temperature has increased to 400 Kelvin. So during the process, a pressure relief valve allows nitrogen to escape, maintaining constant pressure in the tank. So neglecting kinetic and potential energy effects and using the ideal gas model with constant specific heats evaluated at 350 Kelvin, determine the mass of nitrogen that escapes in kg and the amount of energy transfer by heat in kilojoules. So what is given is we have initially a nitrogen tank which is contains nitrogen at 1 meter cube and the pressure initially is at 10 bar and temperature of 300 Kelvin. So this nitrogen is heated till it becomes 400 Kelvin, and during the process you are maintaining the pressure. So assuming the specific heat to be at the mean temperature of between 300 and 400, so at 350 average of at 350 Kelvin, we need to find out how much mass of nitrogen has escaped and how much heat energy is applied. So again, doing a mass balance, we get the rate of change of mass in the system is rho mcv by dt. This is the mass which is exiting, so minus m dot e, it's the flow rate. So integrating, m dot cv is m dot e dt, which is equal to m1 minus m2. So initially m1 and m2 we can find out using ideal gas equation. So this is PV equals mRT. So PV by R, which is constant because pressure volume are constant. So only the temperature is changing. So PV by R is 1 by T1 minus 1 by T2. So that comes out to be 2.808 kilograms. So T1 is 300, T2 is 400. Substituting here, pressure is 10 bar, volume is given 1 meter cube. So the total mass which is escaping from the tank is 2.808 kilograms. And applying again energy balance, the energy coming in minus energy going out equals the rate of change of energy in the system, that is du Cv by dt, which is the internal change of energy of the system, equals the energy which is coming in, just q dot Cv is the heat supplied to the tank, minus uh, energy going out is the energy carried by the nitrogen gas going out, which is m dot E into He. So here so expanding this, so U is m dot m into specific internal energy. So expanding that becomes m du by dt plus u dm by dt, and qcv remains qcv, and He now enthalpy can be written as u plus pv, or pv you can write it as mrt, and m dot E is dm by dt. So since this is specific enthalpy, we get P into specific volume, U plus P into specific volume, or U plus RT. So that's what is written here. So U dm by dt gets cancelled out on the both sides. So what we remain is m du by dt equals q dot Cv plus RT dm by dt. So rearranging, you get the heat supplied to the control volume equals m du by dt minus R dm by dt. So for ideal gas, du is Cv by Cv dt, and with P m is written as Pv by mRT from ideal gas equation. So dm substituting, we get dm to be, with respect to temperature, we get dm to be Pv by R dt by minus T square. So differentiating with respect to temperature, this is what we get. So qcv is Pv by RT Cv dt by the temperature with respect to time, plus for with respect to mass we get Pv by RT R dt by dt. So taking Pv by RT common, we get Cv plus R, which is Cp. So we get Pv Cp by R into 1 by dt by dt. So integrating this, we get Pv Cp by R, which is constant, we can take it out, integrate dt by T from temperature T1 to T2, we get ln T2 by T1. So we know pressure, volume, Cp and R, we also know temperature. So substituting here, so P is 10 bar, volume is 1 meter cube, Cp is 1.041 kilojoule per kg Kelvin, and R is 8.314 divided by 28, and ln T2 by T1 is ln 400 by 300, comes out to be 1009 kilojoules. We'll revisit this problem again. So what we did is, first we found out integrated mass flow rate, find out how much mass is going out, that is written in terms of m1 minus m2. So masses m1 and m2 can be found out from ideal gas equation, which is Pv by RT, and with respect to substituting the values, we found out the total mass which is going out, which comes out to be 2.808 kilojoule per kg. Then we wrote the energy balance equation, which comes out to be 2u Cv by dt equals q Cv minus m dot E He. And then what we did is we expressed u and enthalpy in terms of specific internal energy and pressure and volumes and so on. So u is m dot m into u, so specific u, and then enthalpy is specific internal energy plus RT. So the u terms gets cancelled out. What is left out is the q is equals to m du by dt minus r dm by dt. And then what we did is expressed du as Cv dt. So if you differentiate du with respect to dt with respect to time, we got to get du by dt is Cv dt by dt, because Cv is constant, we are assuming Cv is constant, so Cv dt by dt. So this becomes mCv dt by dt minus then RT. M can be written in terms of ideal gas equation, PV by RT. So in differentiating that, we get with respect to time, we get this PV by R multiplied by dt by minus t square, and substituting that and rearranging, this is what we get, PV multiplied by Cp divided by R into dt by t, and then integrating this, we get the total heat which is applied to the tank, and substituting the values, we get 1009 kilojoules. So next question is, a tank containing 45 kilograms of liquid water initially at 45 degrees Celsius has one inlet and one exit with equal mass flow rates. So liquid water enters at 45 degrees Celsius and a mass flow rate of 270 kilograms per hour. A cooling coil immersed in the water removes energy at a rate of 7.6 kilowatts. So the water is well mixed by a paddle wheel so that the water temperature is uniform throughout. The power input to the water from the paddle wheel is 0.6 kilowatt. The pressure at the inlet and exit are equal, and all kinetic and potential energy effects can be ignored. Plot the variation of water temperature with time. So what is there is you have a tank which contains water, and there is mass which is coming in and going out at same mass flow rate. So mass flow rate which is coming in and going out are same. So whatever is there inside will remain, the mass will remain constant, because which is coming in is going out. So whatever is staying inside, the mass will remain same. So for this tank, you have a cooling coil which is immersed inside, and it removes heat at a rate of 7.6 kilowatt, and this water is well mixed by a paddle wheel so that water temperature is uniform throughout. So the paddle wheel, whatever energy is supplied is accounts for 0.6 kilowatt, and the pressure is constant throughout the tank. In the inlet and outlet, the pressures are same, and the kinetic energy and potential energy can be neglected. So we need to find out how the water temperature varies with respect to time. So what we'll do is we'll apply the control volume to the tank and write the energy balance equation. So energy in minus energy out equals the change in energy of the system, rate of change of energy of the system. So rate of change of energy is du Cv by dt equals the energy in is q Cv and is rejected. So m1 h1 minus m2 h2 and minus q minus w. So Q is rejected here and W work is applied. So again this U can be written as terms of mass into specific volume. So since the mass of the control volume is not changing, dmCV by dt is 0. So what we have is mCV into du by dt, and du by dt can be written as du by d with respect to temperature, and dt by dt, change of temperature with respect to time. And du by dt is nothing but your Cv. So du Cv by dt is mCv into Cv multiplied by the change of rate of change of temperature with respect to time. So substituting this, we get mass of the control volume into Cv into rate of change of temperature with respect to time equals Q minus W plus m dot Cv into change in temperature T1 minus T, because the inlet temperature remains constant at 45 degrees Celsius and outlet temperature is varying with respect to time until it reaches a steady state where the temperature remains constant later on. So initially the bulk of the mass of liquid has to be cooled down. So that's why you initially see a drop in temperature, and it's varying, and after some time the temperature will remain constant. So now integrating this, we get temperature to be C1 exponential minus m dot by m dot Cv into time plus Q dot Cv minus WCV by m dot Cv plus T1. So this is what the temperature expression which we get. So at T equal to 0, T will be T1, and the final expression is this. So just substituting the values here. So Q is 7.6, W is 0.6. So minus 7.6 minus 0.6 divided by m dot C. So 270 kilograms per hour. So 270 divided by 3600 into here C for liquid, Cp for liquid is 4.2. So substituting, we get temperature to be 318 minus 22 multiplied by 1 minus exponential of minus 6t. So if you plot this t in hours, so this is what we get. This is the curve, and it reaches a temperature state of 296, after which the temperature of the bath will remain same. Moving on, next question is, let us consider the tire of a car wheel carrying a load F as shown in figure. To inflate the tube of this tire, we connect it to a reservoir of compressed air whose thermodynamic state is characterized by the pressure PR and temperature TR. During the inflating process, the thermodynamic state of air inside the tire tube goes from initial state 1 to a final state 2. As a result of this process, the wheel hub rises of a height delta H. So for this, the assumption is the thermodynamic state of air contained in the reservoir remains constant. The volume of air contained in the pipe connecting the reservoir and the tire tube is negligible. The strain energy of the tire is neglected. The heat transfer is neglected. The changes of potential energies are negligible. Air can be considered as a perfect gas. So calculate the mass of the air delta M taken from the reservoir. So how much mass is taken from the reservoir to inflate the tire. So this is how the process looks. So you have a reservoir, you have a tire to which it's converted to the tire, and there is a force which is acting on this tire initially. And what they say is, once the mass is filled, the wheel hub rises by a height of delta h. After filling, so what we know is the hub is rising by a height of delta h, which is 0.2 meter. So load which is applied on the tire is 3000 Newton, and CV and R values are given, and the reservoir pressure is 5 bar and temperature is 20 degrees Celsius. The atmospheric pressure is 1 bar, and the tire initial and final states volumes are given. So 0.02, pressure 1.5 and temperature 20, and finally 0.03, pressure is 3 and temperature is not known. So during state 1 and 2 the air is getting filled, but state 1 and 2 is the initial and final states. So applying the first law, we get delta U is some work which is done plus the change in M2 minus M1 into the enthalpy R HR. So delta U is the change in energy of the system equals the Q. This is just the first law expression, du by dt Q minus W plus M in minus M out. So just that. So expression we get W M2 minus M1 into HR. So the work received by the system is 2. 1 is the change in potential energy, and 2 is so what we did is again the same to the similar problem. So work system plus surrounding. So this like that. So work in inflating this tire is 1, which is raising the potential energy of the force which is acting on the hub, and second the work done by into the atmosphere, that is which is exerting the constant atmospheric pressure, pressure A PA. So initially 3000 Newton of force which is acting on the tire, so that is lifted by 0.2, so that gives the change in potential energy, so or F into X. So that is the work done in raising the height. And the second, because the tire is expanding, it is doing some work on the surrounding atmosphere, so that is equals to P into delta V. So that is the total work which is received by the system. Substituting the work in the first equation, say here, so delta U is M2 U2 minus M1 U1 equals the work done minus F delta H minus PA delta V plus M2 minus M1 HR. So U2 is expressed in terms of CV, and HR we can write in terms of CP. So what we get is M2 CVT2 minus M1 CVT1 plus F delta H plus PA delta V equals delta M CP TR. So M2 minus M1 is the mass which is entering the tire. So that is what we need to find out, how much mass is entering the tire. And so delta M now becomes so what we get is CV we can take it common, so CV and multiplying by R we get M2 RT2 minus M1 RT1, which can be written as PV. So that's what is written, CV by R is P2 V2 minus P1 V1 plus F delta H plus PA delta V is V2 minus V1 equals delta M into CP into TR. So what we get is delta M is 56.138 grams. Substituting the values here, we get delta M to be 56.138 grams. So what we did is what is happening is from a reservoir you are inflating a wheel, so that wheel is subjected to a force of 3000 Newton. So that is similar to you have a two-wheeler or a four-wheeler. So each wheel is subjected to the weight of the vehicle. So for a two-wheeler you suppose the weight of uh, the scooter is some kgs, so half of it is acted on two wheels or based on the distribution. So each of the hub experiences some force because of the weight of the vehicle. So what the problem says is uh, initially it is at 1.2 bar and you are inflating the tire, so some amount of air is pumped into the tire, because of which the tire expands and the hub rises by 0.2 meters. And in the process, so you are doing two kinds of work. One, raising the height, for which you need to do some work, and second, because the tire is inflating, it is doing some work on the atmosphere, or the atmosphere is doing some work on. So there are two kinds of work, and if you apply an energy balance to this process, so energy in minus energy out equals energy stored. So rate of change of energy of the system is du by dt, and energy in minus energy out, there is no energy out, so only changes the energy coming in. So there are one which is the work done, and second, so which is work done by the system, and second is the energy carried by the air which is coming in. So that's why work done plus the mass change coming in multiplied by the energy of the air in the reservoir. So m2 minus m1 into enthalpy of the air in the reservoir. So this is what is given, and what we saw is the work which is coming in is doing two kinds of work, and that is F into delta H and P into delta V, and that we substituted here, and then we rearranged and expressed in terms of pressures and volumes, and substituting the values we found out the delta M is 56.138 grams. So final question for today, we have steam enters a turbine with a pressure of 30 bar, a temperature of 400 degrees Celsius. So steam enters a turbine with pressure of 30 bar and a temperature of 400 degrees Celsius and a velocity of 160 meters per second. So saturated vapor at 100 degrees Celsius exits with a velocity of 100 meters per second. At steady state, the turbine develops work equal to 540 kilojoule per kg of steam flowing through the turbine. So heat transfer between the turbine and its surrounding occurs at an average outer surface temperature of 350 Kelvin. So determine the rate at which entropy is produced within the turbine. I think it's better to see it in the next class. I think this on entropy. So this is the final problem for today. We have two heat engines which operate between the same two energy reservoirs, and both receive the same QH. So one engine is reversible and other is not. What can you say about the two Q which is ejected to the lower energy reservoir? So what is there is you get same amount of heat for two engines, but one engine is reversible and other is not reversible, which is an irreversible engine. So what can you say about the heat rejected in both the engines. So what we know is one is reversible, and we know that reversible engines are the efficient engines, the most efficient engines of all the engines which you can develop. So the reversible engine will be more efficient, so it will generate more work. So if you apply first law, Q which is coming in minus Q which is going out will be equal to the work done. So if work done is maximum and both receive same Q, if work is maximum for reversible engine, so your Q rejected will be lower in case of reversible engine, and the Q rejected will be higher in case of the one which is not reversible. So the reversible heat engine can produce more work as higher efficiency than the reversible heat engine, and because of energy conservation, so we get W reversible is QH minus QL reversible, so which states which will be greater, work reversible is always greater than work produced in the reversible engine. So QH minus, so rearranging we get QL reversible is less than QL irreversible. So that's all for today. We have finished the problems which I prepared for today. So we have covered problems on first law, and we have started with some problems on second law. So we'll see some more problems of second law in the next week. So in the first laws we covered all kinds of components, and for a process or a multiple components, how it's applied, and how you apply for unsteady cases, how you apply mass balance and energy balance. So that's what we looked at for first law system for open systems. And then we'll also discussed on the second law, the statements, and give a brief idea on those, and then started with a problem on second law. So we'll look at more problems in the next week for second law systems. So thank you.